Heaviest black hole merger defies stellar formation theory. A groundbreaking discovery, the heaviest black hole merger challenges established theories. In a stunning revelation that has sent shockwaves through the astrophysics community, researchers have identified the most massive black hole merger ever recorded, an event that defies conventional understanding of how black holes are formed. This extraordinary merger involved black holes with masses approximately 100 times that of our Sun, a range that traditional stellar formation theories suggest should not exist. The findings, shared earlier this week, indicate that some black holes may actually form through a process involving multiple mergers, rather than the expected single stellar collapse. Since the groundbreaking detection of the first black hole merger in 2015, the LIGO-Virgo-Cagra (LVK) Collaboration, a consortium of scientists utilizing gravitational wave detectors across the United States, Europe, and Japan, has observed around 300 such mergers. When two black holes spiral towards each other, they generate ripples in spacetime, known as gravitational waves, which can be detected on Earth using highly sensitive instruments. Most of the black holes detected so far have masses around 10 solar masses, a size that aligns well with the theory that massive stars exhaust their nuclear fuel and collapse into black holes. However, not all stars follow this predictable path. Theoretical models suggest that extremely massive stars, those weighing around 200 solar masses, are inherently unstable. The immense energy within the core of such a star can lead to the production of electron-positron pairs, a combination of matter and antimatter that diminishes the star's self-sustaining pressure. This reduction in pressure can trigger a catastrophic implosion, preventing the star from ever becoming a black hole. Consequently, it is believed that stellar collapse cannot yield black holes in the mass range of approximately 60 to 130 solar masses. In a surprising twist, the LVK Collaboration previously detected a merger in 2019 involving black holes with masses of 65 and 85 solar masses, which were at the lower end of this so-called mass gap. This unexpected finding sparked discussions about alternative formation scenarios for black holes, but due to uncertainties surrounding the predicted mass range, it remained plausible that these black holes originated from some modified stellar collapse process. Now, the LVK Collaboration has taken the conversation to a new level by identifying two even heavier black holes, one of which falls directly within the mass gap. This event provides compelling evidence that black holes within the mass gap can indeed exist, states Stephen Firehurst, a spokesperson for the LIGO Scientific Collaboration from Cardiff University in the UK. The newly identified event, designated GW2-31123, was observed in November 2023 by the two LIGO observatories in the United States. The gravitational wave signal detected was in the low-frequency range, indicating that the black holes involved were on the heavier side. Additionally, the signal was notably brief, lasting only 1/5 of a second, making its interpretation more complex, as explained by LVK member Sophie Binney from Caltech. The collaboration employs waveform models to extract parameters such as mass, orbital orientation, and distance from the signals. The analysis is more uncertain because you have less information to start with, Binney notes. The best fit for this merger indicated that the two black holes had masses of 103 and 137 solar masses, resulting in a final black hole with a mass of 225 solar masses. Due to the short duration of the signal, the researchers were unable to determine the precise location of the event in the sky. Binney presented these exciting results at the GR Amaldi meeting in Glasgow, Scotland, earlier this week. Astrophysicist Davide Gerosa from the University of Milano Bicocca, who was not involved in the study, expressed enthusiasm about the findings. This is indeed thrilling news. When we first detected gravitational waves a decade ago, we were astonished to find black holes of 30 solar masses. Now, we are observing black holes exceeding 100 solar masses, which is simply spectacular. This leads to a pivotal question. How do these colossal black holes come into existence? One potential explanation is that these black holes arise from hierarchical mergers, Binney explains. This model suggests that earlier generations of black hole mergers create exceptionally massive black holes, which then merge with other heavy black holes. It's akin to a family tree of black holes, she adds. However, a significant challenge for this model is the likelihood of merged black holes encountering one another. Typically, a merger event imparts a recoil kick to the resulting black hole, potentially ejecting it from star-rich regions where further mergers would be anticipated, as Binney elaborates. An intriguing aspect related to hierarchical merging is the rotation, or spin, of the black holes around their axis. In the standard stellar collapse scenario, the two merging black holes would have formed within a binary system, leading to aligned and relatively small spins. Indeed, most mergers recorded by the LVK Collaboration exhibit small spin values for the incoming black holes. However, the final black hole produced from the merger should possess a relatively large spin value, as it effectively absorbs all the orbital angular momentum from the rapid motion of the merging black holes, according to Gerosa. The researchers analyzed the spins of the two merging black holes in GW 231123. Although the spin values come with significant uncertainties, ranging from 20% to 50%, both black holes appear to be spinning close to their maximum allowed values, one at 80% and the other at 90%. Such elevated spins imply that these black holes likely originated from previous merger events. However, Gerosa points out that the observed spin values may be slightly higher than expected. The typical prediction for spins in the hierarchical merger scenario is around 70%, he notes. He speculates that as modelers continue to analyze the data, the estimates for the observed spins may be adjusted downward. Another scenario that the LVK Collaboration is considering is the possibility of a massive star merging with another star, thereby circumventing the pair creation instability. However, these models struggle to account for the high spin values observed in this case. While the precise formation mechanisms of these black holes remain uncertain, scientists may be able to infer their formation environments. Theorist Rosalba Perna from Stony Brook University in New York, who was not part of the study, suggests that the GW 231123 merger likely occurred in a setting where star density is sufficiently high to facilitate frequent black hole interactions or where the surrounding medium is dense enough for black holes to accumulate significant additional material. Active galactic nuclei come to mind as a potential environment, she remarks. This groundbreaking discovery not only challenges our understanding of black hole formation, but also opens the door to new questions and discussions. How do you think these massive black holes came to be? Do you agree with the hierarchical merger theory, or do you have alternative explanations? Share your thoughts in the comments. Astronomers detect the most massive black hole collision ever seen. In a groundbreaking discovery, astronomers have identified the most massive collision of black holes ever recorded, a monumental event that has captured the attention of the scientific community. This extraordinary merger, known as GW 231123, involves two black holes, each boasting a mass greater than that of 100 suns. The detection of this event was made possible by the Laser Interferometer Gravitational Wave Observatory, LIGO, which consists of two identical facilities located in Livingston, Louisiana, and Hanford, Washington. These instruments picked up subtle ripples in the fabric of space-time, known as gravitational waves, generated by the violent clash of the two black holes. Gravitational waves were first predicted by the renowned physicist Albert Einstein in 1915 as part of his theory of relativity. At that time, he believed that these waves would be too faint to ever be detected by human technology. However, in a remarkable turn of events, LIGO successfully detected gravitational waves for the first time in 2016, confirming Einstein's theories once again. This monumental achievement led to significant recognition for three scientists who played pivotal roles in the development of what has been informally referred to as a black hole telescope. Since that initial detection, LIGO, along with its counterparts, Virgo in Italy and Kagra in Japan, has recorded approximately 300 black hole mergers. Mark Hannum, the head of the Gravity Exploration Institute at Cardiff University in the UK and a member of the LIGO Scientific Collaboration, remarked, "These incredible detectors are the most sensitive measuring instruments ever created by humanity. We are witnessing the most extreme and violent events in the universe through the tiniest measurements we can achieve." What sets GW231123 apart from the other 300 black hole mergers is not only its unprecedented mass, but also the unique characteristics of the individual black holes involved. Charlie Hoy, a research fellow at the University of Portsmouth in the UK and a fellow member of the LVK Scientific Collaboration, noted, "The individual black holes are remarkable because they exist in a mass range that we do not expect to arise from the death of stars." He further explained that these black holes are likely spinning at nearly the maximum speed possible, presenting a significant challenge to our current understanding of how black holes are formed. Gravitational waves provide the only means for scientists to observe collisions in binary systems where two black holes orbit one another. Prior to the advent of gravitational wave detection, there was even skepticism about the existence of black hole binaries, as these enigmatic objects do not emit light or any form of electromagnetic radiation, rendering them invisible to traditional telescopes. According to Einstein's theory of general relativity, gravity is a distortion of space and time, causing objects to navigate through curved space. When objects move at high velocities, such as rapidly spinning black holes, the curvature of space generates ripples that propagate outward like waves. Hannum described these gravitational waves as ridiculously weak and acknowledged the limitations in the information they can provide. For instance, there is uncertainty regarding the distance of GW231123 from Earth, which could be as far as 12 billion light-years away. However, he is more confident in estimating the masses of the two black holes, which are believed to be approximately 100 and 140 times that of the Sun. These mass figures raise intriguing questions. Hannum explained, "There are established mechanisms for black hole formation when stars exhaust their fuel and collapse. However, there exists a mass range where we theorize that black holes cannot form through this process. The black holes in GW231123 fall squarely within this mass gap, prompting questions about their formation and making them particularly fascinating." The mass gap that Hannum refers to spans from about 60 solar masses to roughly 130 solar masses. Since this is a theoretical range that has not been directly observed, there is some ambiguity regarding its boundaries. If the black holes in GW231123 indeed occupy this gap, it suggests that they did not form from collapsing stars, but rather through an alternative mechanism. In a recent study published on the open-access repository Arxiv, Hannum and his colleagues proposed that the mass gap could be explained if the two black holes resulted from previous mergers rather than from dying stars. This is a concept that has been discussed in the past, and we have seen hints of it before, he stated. In this scenario, a chain reaction of black hole mergers could occur, leading to the formation of increasingly massive black holes. Hannum elaborated, "You can have a process where more and more massive black holes are created. Since the black holes in GW231123 appear to be at masses that cannot be achieved through normal mechanisms, this strongly suggests that successive mergers are taking place. If this hypothesis is validated, it would imply the existence of an unexpected population of black holes that fall between those formed from the deaths of massive stars and the supermassive black holes typically found at the centers of galaxies." Dan Wilkins, a research scientist at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University, who was not involved in the GW231123 discovery, remarked, "Gravitational waves are providing a fascinating glimpse into the world of black holes and unveiling some truly intriguing mysteries. Before the era of gravitational wave astronomy, we could only detect black holes that were actively consuming material, producing a bright light source. Gravitational waves are revealing a different segment of the black hole population that grows not by accreting material, but by merging with other black holes." Another astonishing aspect of GW231123 is the rapidity with which the two black holes are spinning around each other. Hoy noted, "Thus far, most black holes detected through gravitational waves have exhibited relatively slow spins. This suggests that GW231123 may have formed through a different mechanism compared to other observed mergers, or it could indicate that our models need to be revised. Producing such high-speed spins is challenging, but they also lend credence to the idea that these black holes have undergone prior mergers, as scientists would expect previously merged black holes to exhibit faster spins, according to Hannum. Sophie Binney, a postdoctoral researcher at Caltech and a member of the LIGO-Virgo-Cagra collaboration, stated, GW231123 poses a challenge to our gravitational wave signal models, as it is complex to simulate such rapid spins, and it stands out as an extraordinary event that is difficult to interpret. What surprises me the most is how much we still have to learn about gravitational waves. I genuinely hope that in the future, we can observe more events similar to GW231123 to enhance our understanding of these systems. Previously, the record for the most massive black hole merger was held by GW190521, which was only 60% the size of GW231123. However, Hannum suggested that even more massive mergers could be discovered in the future, potentially observed through even more precise instruments that may become available in the coming decades, such as the proposed Cosmic Explorer in the United States and the Einstein telescope in Europe. This remarkable discovery opens up new avenues for understanding how black holes can form and evolve, according to Imre Bartas, an associate professor at the University of Florida who was not part of the research. He added, "It also highlights the rapid advancement of gravitational wave astronomy. In less than a decade, we have progressed from the first detection to exploring territories that challenge our most robust theories." While he concurs that previous mergers could account for both the high mass and the rapid spin of the black holes, other possibilities include repeated collisions within young star clusters or the direct collapse of an exceptionally massive star. However, he noted that these alternatives are less likely to produce black holes with such fast spins. Zoltan Hyman, a professor at the Institute of Science and Technology Austria who was also not involved in the discovery, stated, "It is quite reasonable to interpret the black holes in GW231123 as remnants of one or even multiple generations of prior mergers." This idea was proposed immediately after the first LIGO detection of a black hole merger, but this new merger is particularly challenging to explain through other means. Future detections, he added, will reveal whether this heavyweight encounter was an isolated incident or merely the tip of a much larger iceberg. Scientists stunned by massive black hole that defies physics. A cosmic heavyweight just threw a curveball at our understanding of physics, and it's leaving scientists scratching their heads. Imagine discovering a black hole so massive, it defies every rule we thought we knew about how stars live, die, and collapse. That's exactly what happened with GW231123, a newly detected black hole that's rewriting the playbook on astrophysics. But here's where it gets controversial. This monster shouldn't exist at all. Let's break down why this discovery is shaking up everything we thought we knew. Over the past decade, the LIGO-Virgo-Cagra, LVK, network has cataloged hundreds of black hole mergers, each one a glimpse into the universe's most violent events. But nothing compares to GW231123. This colossal black hole, formed from the collision of two behemoths, tips the scales at 225 times the mass of the Sun, a staggering leap from the previous record holder, GW190521, which clocked in at 140 solar masses. To put that into perspective, if our Sun were a grain of sand, this black hole would be a boulder the size of a city block. And this is the part most people miss. The two black holes that merged to create it were already straddling a forbidden zone in astrophysics. Back in 2015, LIGO stunned the world by capturing the first gravitational waves, a cosmic ripple caused by the collision of two black holes. That event birthed a black